Let's break down Atlantis. At its core, it's an automated cyber reasoning system, and it was engineered from the ground up to find, prove, and even fix software vulnerabilities, all using large language models. So, how well does it work? Well, at the AI Cyber Challenge Finals, Atlantis, competing under the name Team Atlanta, took first place. It didn't just win, it dominated, finding 43 out of the 70 total vulnerabilities. That score put it way ahead of the competition. So we're going to look under the hood. We'll start with a high-level overview of the system, then dive into the vulnerability discovery engines for C, C++, and Java. After that, we'll look at the automated patching agents, and finally, we'll cover some of the really interesting 0 days it uncovered.
All right, first up, the big picture. Let's talk about the overall system architecture and how it managed its resources, especially under the tight constraints of a competition.
The whole system was built with 4 key requirements in mind. First, it had to process multiple challenge projects at the same time. Second, it needed a fail-safe architecture, so one failure wouldn't bring the whole thing down. Third, it had to use every last drop of its LLM and cloud budgets. And finally, everything needed to be fully observable with open telemetry for logging.
The workflow itself is a completely hands-off, automated pipeline. It all kicks off when the web server gets a new challenge. Right away, a dedicated manager instance spins up just for that task. From there, the bug-finding modules start hunting for vulnerabilities. The moment they find a proof of vulnerability, or a POV, it gets verified and passed over to the patching modules. A patch is generated, bundled up with the POV, and the whole package is submitted. Done.
And that $50,000 LLM budget, it was allocated very strategically. You can see the biggest chunk, over 37%, went to Atlantis Multilang, which is a module for generating input using multiple different LLMs. The patching module got about a quarter of the budget, while the C and Java-specific modules each got a little under 19%. It's a clear breakdown that prioritizes the most LLM-heavy parts of the system. Okay, now let's get into the nitty-gritty, the vulnerability discovery engines. Atlantis used totally different, specialized approaches for C and C++ versus Java. For C and C++, the star of the show was a directed, grammar-based fuzzer they called Bullseye. The way it works is pretty cool. It does static analysis to pick out key landmarks in the code, and then calculates the distance to them. So during the actual fuzzing, it can prioritize inputs that are getting closer and closer to those hard-to-reach spots. And it wasn't just a neat idea, it really performed. When they benchmarked it against the well-known AFL Plus fuzzer, Bullseye was faster to find bugs on 7 out of 11 targets. And even better, it found more unique crashes on 9 of those 11 targets. Now, for Java, the strategy had to be completely different. You see, a lot of Java vulnerabilities don't cause a nice, clean crash. Instead, they come from the unsafe use of sensitive APIs, what we call sinks. So, naturally, Atlantis Java used a sink-centered approach.
This approach breaks down into a 3-step flow. First up is sink exploration. This is where the fuzzers are just trying to satisfy all the path constraints to even reach one of these sensitive API calls. Next is sink management. Think of it as a traffic controller, a central component that's tracking the status of every sink. Is it unreached, reached, or already exploited? And it's allocating resources based on that. Finally, if a sink is reached but not yet exploited, the sink exploitation phase kicks in using a special agent called XKit.
And this XKit agent was incredibly effective. It had an 81.3% success rate. That means for vulnerabilities where the fuzzers managed to reach the sink, XKit was able to generate a working exploit more than 4 out of 5 times. So finding vulnerabilities is one thing, but Atlantis could also fix them, and it did that using a whole suite of automated patching agents working together in a multi-agent framework. A really key part of this was a component called Prism. It uses a kind of team-based structure. You've got a supervisor agent that coordinates 3 specialized teams, an analysis team to really understand the bug, a patch team to generate and review code fixes, and an evaluation team to test the patch. These teams work in a loop, over and over until they produce a valid patch. The results from a preliminary round speak for themselves. The top patching agents were hitting success rates of 97 to 100%. The Vincent agent got a perfect score, with multi-retrieval and Prism right behind it. It just goes to show how effective it is to throw a diverse set of specialized agents at a problem like this.
But, patching wasn't always a simple fix. Take this Nginx double-free vulnerability. The LLM agents first came up with a patch that just nullified a pointer. Sure, that fixed the immediate symptom, the crash, but it missed the real issue. The correct patch also needed to finalize the HTTP request and return a proper error code. It's a perfect example of why you need a deep understanding of the application's logic, not just a way to prevent a crash.
All right, let's wrap up by looking at the real-world impact. We're talking about novel, previously unknown zero-day vulnerabilities that Atlantis discovered during the competition. First up, a zero-day in SQLite 3, which, as you know, is one of the most widely used database engines on the planet. This exact SQL command here, with its incomplete tokenizer argument, was enough to trigger an off-by-one read in the FTS5 full-text search module. So what was the root cause? Well, the tokenizer was expecting arguments to come in key-value pairs. By providing a key without a value, the fuzzer tricked the code into reading past the end of the argument array, and that, of course, led to a crash.
And the patch Atlantis generated is just a simple one-liner. All it does is add a bounds check to make absolutely sure that I+1 is less than the total number of arguments before it tries to access that element. Simple and effective.
But it wasn't done with SQLite 3. The system found another zero-day, this time in the LSM1 extension. This one was a use after free. What was happening was a data pointer was being cached, but under certain conditions, a buffer could be reallocated without clearing that pointer. This left the door open for the code to later read from that freed memory.
And again, the fix was subtle but crucial. It involved moving a single line of code, the one that clears the stale pointer, outside of a conditional block. This one change guarantees the pointer is always reset no matter what, which completely eliminates the use after free bug across all possible code paths.
When you see automated systems like Atlantis not just finding but also fixing these kinds of complex vulnerabilities, it really makes you think. It points to a future where the role of the human security analyst is definitely going to evolve.